few weeks, I guess, is to use this graphic tablet, and I hope it will be understandable in any case. So I'm lecturing with this method the other course, so it should not be a big problem. So now I will share the screen. Just a moment. Present now. A window. What happened here? There should be Wacom space in space. Questo si vede. Present now. Window. Okay. Okay, so now you should see something which is a white board. Okay. So it is understandable what I'm writing?
Yes. Yes.
Okay, so we can proceed. Okay, so last time what we did was to sort of exercise in which we had well, any possible particles. Each of them could be in k states. We saw already that in this case, the total number of arrangements, is basically k to the power of n. For k equal 2, indeed, it was 2 to the power of n for the case of spin 1/2 lattice that we did last time. And then for the Boltzmann entropy, for such a system, S is kb log of the total number of configurations which are comparable with my thermodynamical equilibrium.
Mi scusi,
Yeah?
puoi scrivere leggermente più grande?
Okay.
Grazie.
Okay. Which is kb log of k to the power of n, which is kb n log of k. Okay. So now this is the Boltzmann entropy. Then we introduced another quantity, which is the Gibbs or Shannon entropy, which was basically the following. I had a certain configuration which is compatible with my constraints, in which I have n1 particle in state 1, n2 particles in state 2, and nk particles in state k, under the constraints that the sum from I to 1 to k over ni is equal to n. And then we said, okay, the total number of ways to arrange n1 particle, n2 particles, and k particles in those boxes is provided by omega, which is n factorial divided by n1 factorial, n2 factorial, blah, 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 and k factorial. Okay, and then we said, okay, we define the Gibbs or Shannon entropy as the log. So let me put here for just a moment Gibbs. G stands for Gibbs. is just, let's put also kb equal to 1, is just the log of omega, which is the log of n factorial and 1 factorial and k factorial. And then we said, okay, if I take the limit of large n and of ni to plus infinity, so large number of particles, then we get what actually is considered to be the definition of the Gibbs or Shannon entropy, which is Sg equal to minus n sum from I to k of pi log of pi, where pi is ni divided by n. Okay, this was the result when applying the usual Stirling approximation. Then we said, okay, let us consider the most probable set of n1 and k under, this is important, under the constraint that the sum of ni is equal to n. Okay, so let's say that let's consider the Gibbs entropy associated with the most probable configuration of n1 and k. Under the most probable under the constraint that the sum of ni is equal to n. Okay, so we have a situation in which we have to maximize a function of several variables by respecting a constraint. And so to do that, we did the Lagrange multiplier. We applied the Lagrange multiplier method, and at the end, what we concluded is that the most probable configuration is the one for which pi is equal to 1 over k. So all probabilities are the same. And let me change page. And now if I compute the Gibbs or Shannon entropy associated to the most probable configuration, or the most probable, then I have to do minus n sum over 1 over k log of 1 over k, which at the end provides basically n log k. This calculation was done last time. So exactly the Boltzmann entropy. Okay. So the message is the following. In principle, I have to consider all the possible configuration or ni and k, which means suppose that I have, I don't know, 100 particles. Then I put 1 particle in 1, 2 particles in 2, etc. Now, of course, I have a certain number of possible configuration, which must be compatible with the constraint that the total sum is equal to n. And basically, in the case of just one constraint, the combinatorial is not very difficult. Actually, can be computed easily by using the formula that we said last time, which was the following. Let me write it again. But the formula that one can use is the following: k to n is equal to sum n1 to nk under the constraint n1 plus n2 nk is equal to n of n factorial divided by n1 factorial nk factorial. Okay, so in this case, for just one constraint, actually, the combinatorial is not very difficult, and this is provided by this formula here. Okay, first of all. Second, what we learned with this exercise is basically what we already know from the case of two possible states, namely that considering the most probable configuration or considering all the possible configurations compatible with the constraints is basically the same for what concerns the entropy. Namely the Boltzmann entropy, which is KB log of all the possible configurations, which will be the configuration compatible with my thermodynamical equilibrium. It can be computed by just considering the most probable configuration, so without considering all the possibilities. So this is actually a very interesting result, because that means also that the most probable configurations will occupy basically the big part of the phase space. What will be the phase space in a few lectures? Okay. So then, in a system which is in thermodynamical equilibrium, basically, I get that the statistical mechanics interpretation is that the thermodynamical equilibrium corresponds to the most probable configurations, basically, incompatible with the constraints, of course. And then also we provided a sort of interpretation in terms of information theory, in the sense that the configuration for which the pi are equal to 0 but for 1 is the configuration of zero entropy, zero Gibbs entropy, which corresponds also to the case in which sending a message is not does not provide any new information. Whereas in the case in which all the pi are equal to 1 over k, sending a message, of course, provides information because it breaks the degeneracy. Okay, so now let's make the things more complicated, and now consider a system which is more similar to a physical system. Namely, let us consider now the case of independent and localized particles n, and let us consider the case in which we have n epsilon 1, epsilon 2, blah 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 energy levels. And let us suppose, which is typically the situation in physical systems, that the spectrum is unbounded from above. Okay, so basically I have an infinite number of energy levels, and then I will arrange, so let's say this epsilon 1, epsilon 2, and so on and so forth, and suppose that I will have n1 particles in epsilon 1, n2 particles in epsilon 2, and 3 particles, etc. Okay. Now, suppose that the system has a certain number of particles, which is n, so therefore I have the first constraints that needs to be fulfilled is that the sum over ni is equal to n. This is the first constraint. But now the situation is more complicated. If I add another constraint, which is the following, let me change page. So let me write it again. I have the sum over ni is equal to n. I suppose now that we have a fixed total energy. Total energy fixed. Let's call it E, and this will be the sum over I, consider that I'm not writing the numbers on which I runs, because they go from 1 to plus infinity, basically. Okay, I don't have a bound on the energy levels. And this total energy will be Ni times epsilon I. So now, in this case, what we'll consider is what we want to compute is compute the total entropy, the entropy of the Boltzmann entropy, okay, S. And in principle, to compute this entropy, one has to do the KB log of the total number of configurations compatible with the constraints. Now the constraints are 2. And therefore, the combinatorial that was in the previous case easier, in the sense that I had just one constraint, and I can use the fact that k to the power of n is the sum of all the possible configuration of the binomial, well, of the multimonomial coefficients. In this case, the situation is more difficult. So in principle, it S should be kb the log of omega, where omega is the sum over all the possible values of Ni, and I'm writing it this way because Ni is not bounded, it can be N1, N2, and infinity, of the n factorial and 1 factorial, blah, blah, blah. Now, with 2 constraints, so the sum over Ni is equal to n, and the sum over Ni epsilon I is equal to E. So now the combinatorial now is much more complicated, because I have an infinite number of energy levels, and then I have also 2 constraints and not just 1. But we can use the lesson that we learned for the previous case. So instead of computing all the possible configuration, let us consider the most probable one. And for what we learned before, the entropy S is actually kb the log of, let's call it omega max, where omega max is the configuration with the highest probability. Okay. Now, so to do this calculation, the thing is the following: omega of Ni. Let me see how I wrote it. Yes, in general is n factorial and 1 factorial, etc. So when I do the log of this quantity, and I get, as usual, so as in the previous case, the result that is n of n minus 1 over Ni log of Ni. Is just the same as before. Just the only difference that n1 and 2, so I have an infinite number of levels in this case, but computing the, if you want, this is basically the Gibbs or Shannon entropy provides the same result. So n log n minus the sum over I of Ni log Ni. Okay. So now what I have to do is to maximize with respect to Ni, so to the set of arrangements with 2 constraints. Which are the constraints of conservation number of particles and the constraint of conservation of energy. So let me write it here. So what I have to do is to consider again the method of Lagrange multipliers, but now with two constraints. And then to do the calculation, I have to consider the following functional form: n log n minus sum of I and which is the function that I have to maximize. And then I have to add the constraints, and let's write them as alpha sum y of ni. So here I should put the number of particles n, which actually is not needed because now I'm going to do a derivative, but let's put it in any case. Then I have a plus beta, two Lagrange multipliers in this case, sum or ni epsilon I, and here I have minus e. And I have to maximize. So derive with respect to ni and put 0. Okay. So when doing the derivatives, what I get is minus the log of ni minus 1. Then I have a plus alpha plus beta epsilon I plus beta epsilon I equal to 0, from which I can get ni, from which I can get that the value of ni is provided by an exponential of e to the beta epsilon I, and then I have a normalization which is e to the alpha minus 1. Okay. Now, as an opposite to the previous case, the case that we just repeated a few minutes ago, now the ni are not, well, depends on epsilon I. In the previous case, we had only one constraint, and the most probable configuration was the one in which all the states had the same probability. In this case, actually, it's not the case anymore, because I have that the probability of a single state actually depends on the energy associated at that state. Okay. Actually, I have a factor here which is called Boltzmann factor. Boltzmann factor, which is telling me that the probability of a certain energy level is proportional to e to the beta epsilon I, where beta must be determined, it's not determined. Of course, now I have to add the two constraints in order to find the values of alpha and beta. And therefore, what I need to write is that n must be the sum over ni, which means that e to the alpha minus 1 sum over beta epsilon I. So this is one. Let me write also the log of n, which will be useful in a moment. So the log of n is the log of e to the alpha minus 1 sum over I epsilon beta. And then I have the constraints and the energy. The energy was the sum of epsilon I and I, which is the exponential of alpha minus 1 epsilon I and e to the beta epsilon I. Okay. Now, what is telling Boltzmann? Boltzmann is telling that the entropy is Kb, the log of the total number of configuration, but in this case, we just consider max, omega max, from what we had said before. And so I just need now to introduce, to compute the omega max, well, the log of omega max by introducing the ni that I just found. Okay, so then this S is equal to Kb, which can be collected outside. Then I have the log of omega max is n log n minus the sum of ni log of ni. And now I can substitute the ni that I just found. So this is Kb sum of n log n, sorry, n log n. Then I have a minus vado capo, minus ni, sorry, minus the sum of Ni. What is Ni? Ni is e to the alpha minus 1 e to the beta epsilon I, and then I have the log of this quantity. So the log of alpha minus 1 is beta epsilon I. Let me close this. Okay. Okay, let me change page. So what I get now is that I need to do the log of these two quantities. Okay, so let me write it again. This is KB. Then I have n log n minus the sum of Ni log of Ni. So I have e to the alpha minus 1 e to the beta epsilon I. Then I have the log of this quantity. And when I do the log, I have alpha minus 1 plus beta epsilon I. Okay, is equal to KB n log n. Then let me see how to arrange this term. Then I have alpha minus 1 sum of epsilon e to the beta epsilon I. Let me check if this is correct. Alpha minus 1, yes, and then I have also alpha minus 1. And then I have the other term, which will be minus beta that can be collected. And then I have the sum over I e to the alpha minus 1 epsilon I e to the beta epsilon I. Okay, maybe it should be correct. Let me check. It's not very clear with this board. Beta epsilon I, alpha minus 1 minus beta epsilon beta I. Okay. Okay. Now, what to do? Okay, so here this is n, because it's the sum over the Ni, so this is just n, whereas this is energy, so this is beta times energy. So therefore I have Kb, then I have n log n and log. Well, now the log of n is actually the log of e to the alpha minus 1 times the sum of I epsilon beta e to the beta epsilon I. Here I have just substituted the log of n is the log of that bracket for what I said before. So n log of epsilon I, yes. Then I have a minus 1, alpha minus 1 times n minus beta. Okay. And then, of course, now I can write this as n alpha minus 1 plus n log of sum over I of e to the beta epsilon I minus alpha minus 1n minus beta e, and this drops. Then I'm left with the following expression that S is equal to Kb, and then I have n log of e to the beta epsilon I minus beta e. Okay. Calculations are easy, just one needs to do it slowly. Okay. So I have the following expression for the entropy, for the Boltzmann entropy. Now let us remember which is the link between entropy, energy, and temperature. Well, I know that the derivative of S with respect to U, fixed number of particles and fixed volume, is 1 divided by the temperature. Now U was the internal energy. In this case, is coincident with the total energy. On this I will comment later on when we will do the canonical ensemble. So basically in this case, what we are going to get is what is called microeconomical ensemble for independent and localized system, in which the total energy is fixed. And in the case in which the total energy is fixed is actually the case in which the internal energy is fixed and it is constant, is not fluctuating. Okay. So let me basically switch between U and E because they are the same quantities in what is going to be called microeconomical ensemble. Okay, so this equation now provides the link between the Boltzmann entropy that we derived from the microscopic theory with the typical thermodynamical quantity, which is the temperature. Okay. So now I have to do this derivative. So the derivative of S with respect to E at fixed number of particles and fixed volume. Actually, the volume here does not play any role because they are localized system. Now this derivative of S with respect to beta, derivative of beta with respect to E by using the chain rule. And that means that I have Kb, which is outside, derivative of beta with respect to E times Kb. And then I have to do the derivative with respect to beta of the expression that I have there, which is n derivative with respect to beta of the log of the sum of I e to the beta epsilon I. Then I have a minus beta, sorry, minus E minus beta derivative of E with respect to beta. Okay. Because beta and E are dependent. Okay, so E is a function of beta because beta is the Lagrange multiplier associated with the conservation of energy. Okay, so now I just need to do the calculation for this Kb derivative. Kb can be take it outside again. Then I have a derivative of beta with respect to E n, derivative of beta with respect to E n, derivative of beta of log of the sum of E to the beta epsilon I. Then I have a minus E derivative of beta with respect to E. And then I have minus beta. Where I'm considering the fact that when I'm multiplying this term and this term here, I have 1, and then I have beta left. Now it is easy to realize actually that this is minus beta kb plus kb the derivative of beta with respect to E. Then I have here, I have to do the derivative of the log of the sum. So therefore I will have in the denominator the sum over I of E to the beta epsilon I, whereas at the numerator I will have the sum of I and deriving with respect to beta, so epsilon I E beta epsilon I. Okay, times n, which was outside, and then I have a minus E. Okay, so I'm collecting derivative of beta with respect to E, and then and put it outside, and then I have basically just what is left in the bracket. Okay. Now it is easy to realize that it is actually zero if I is 0 because remember that n, in fact, n was e to the alpha minus 1, the sum over I of e beta epsilon I. And therefore, when I put this here, I get the denominator cancelled with the numerator, then I have an alpha minus 1 times the sum, which is just the energy. Okay, remember these two relations. So therefore, this is equal to 0. And then I conclude let me change page, from which I conclude that 1 over t, so what I'm computing is the derivative of S with respect to E, fixed number of particles and fixed volume, which is 1 over the temperature. I will just say that this is equal to minus beta, from which beta is equal to 1 minus 1 divided by kBt. Okay. Therefore, Ni is proportional, apart from the constant alpha, which is a normalization constant, is proportional to e to the minus epsilon I divided by kBt, which is something that you probably have already seen many times. Now, this is the Boltzmann factor. Boltzmann factor. Okay. So the Boltzmann factor provides basically the probability, if you want, of occupation of energy level at epsilon y in this situation. Okay, the situation is that you have a total number of particles which is conserved and the total number of energy which is conserved. Okay, so the interpretation of Ni is basically the following: is the probability, but can be also considered in this way. N is equal to e to the alpha minus 1 sum of I e to the minus epsilon I divided by kBt. And now if I do Ni is e to the alpha minus 1 epsilon I kBt. And then I divide by n. I see that this is basically the fractional, well, it's a probability, no? Of course, it's a probability of occupation of state I. Okay, because it's the number of particles in the state I divided by the total number of particles. Okay, this of course drops. And I can introduce a quantity. Let me now change, let me call 1 divided by kBt, let me call it beta, by definition, which is not the same beta as before. I have an additional minus. It's very useful for to consider beta as a variable for the reason that will be clear in a moment. And then let me call beta m the sum over I of e to the minus beta epsilon I, which is what we have at the denominator. This function here is called microeconomical partition function. Partition function for independent and localized systems. What means independent and localized? I have several energy levels that corresponds to the spectrum, if you want, of the Hamiltonian, and then I'm just putting particles in these energy levels. I'm not talking about momenta of those particles, so I can imagine that it is like system of lattice of speeds, for instance. Okay. Well, this function is called microeconomical partition function for these independent and localized systems. And then I see also that the total number of particles is basically proportional to n, because n is just e to the alpha minus 1 times this function here. Moreover, when I compute the ratio between e and n, the ratio is e to the alpha minus 1 sum over I. And here I have minus 1 sum over I of e to the minus beta epsilon I. Of course, this drops. And this quantity, it is actually minus the derivative with respect to beta of the log of zeta m. Okay. Minus the derivative with respect to beta of the log of zeta m. Okay, divided by n. No, because when I do the zeta m and the log and the derivative of the log, of course, I have the denominator 1 over denominator. I have the sum, and then at the numerator I will get epsilon I as coefficient. So what is this quantity here? Is the energy per particle, or is the average energy per particle, which, as you see, can be computed once I have the microeconomical partition function. So, well, this is a quantity, but also the entropy now can be computed starting from the microeconomical partition function. Indeed, we wrote before that the entropy, it was equal to Kb, then I had an n log.
Sorry, prof.
Sì, ho dimenticato il foglio, giusto?
Sì, appunto. Adesso
Yes.
perfetto, grazie.
Now consider that now let's compute the entropy. We arrived at some point, we wrote that the entropy is Kb, and then I have the log of the sum over I of e to the minus beta epsilon I. Now, do not get confused with the minus, because previously the beta was the Lagrange multiplier, which was undetermined. Now beta is 1 over kbt. And then the formula is, the correct one is with the minus, is 1 minus kbt. Okay. Sum over blah, blah, blah. Then I have a plus beta. This was the function that I wrote before, which can be also rearranged in the following way. This is kbn. Now this is the log of the microeconomical partition function. So this is the log of zeta m plus e divided by t. Okay, so this is the entropy, kbn log of zeta m. And then I can also compute the Helmholtz free energy. The Helmholtz free energy was U minus Ts, which in this case coincides with E minus Ts. And therefore, the Helmholtz free energy is, well, I need to take the entropy multiplied by T, and then I have a minus, and then of course the energy drops, and I'm just left with kbn kbnt log of zeta m. That should be the correct one. Okay. kbn kbnt log zeta m. Okay. So you start to see that once we know the microcanonical partition function for this system, we can derive, for instance, the energy per particle or the average energy per particle by just doing a derivative with respect to beta. I can derive the entropy. The entropy is just proportional to the log of the canonical partition function times n plus T. And then I can get also the Helmholtz free energy. Okay, so this partition function, zeta m, is basically the link between microphysics and thermodynamics. And this is exactly the aim of statistical mechanics, of trying to reproduce or to justify and to go beyond actually thermodynamics, starting from the microphysics. Now, in this case, the microphysics is very simple in the sense that I have just said that I have a certain number of particles. I'm not saying anything about the Hamiltonian of those particles. I'm just saying that I have a certain spectrum, so with certain energy levels, and then I'm occupying these energy levels. Okay. So now we will see an application of this microcanonical partition function for independent and localized system just in a moment, which is the Einstein model of solids. I just want to comment on a possibility that what happens in the case in which the spectrum is not bounded from above. In that case, there could be very weird situations in which the temperature could be negative. And this is one argument that I gave last year as a possible, let's say, argument for the exam. But this year, maybe I will do a written exam. So I don't know. I still have to decide on that. It depends on how many exercises we will be able to do. Anyway, well, suppose that we just have two energy levels. So epsilon 1 and epsilon 2. The two energy levels example is a paradigmatic in the sense that is used many times because it is a very useful system as much as the harmonic oscillator. The two energy level example in statistical mechanics is very rich of insights. So suppose that we just have two energy levels, epsilon 1 and epsilon 2, and suppose that all the particles are on epsilon 1. Well, of course, let me make a comment, and let me make it now. At the thermodynamical equilibrium, of course, the ratio between the particles in level 1 and the ratio and the particles in level 2 is provided by N1 divided by N2, which is the Boltzmann factor, epsilon 1 into the minus epsilon 2. This is at the thermodynamical equilibrium because these occupation numbers were found by maximizing the probability of that configuration, which is exactly the thermodynamical equilibrium. Now let me go a little bit beyond thermodynamical equilibrium and let's consider for a moment what happens if all the particles are in epsilon 1 and or the case in which all the particles are in epsilon 2. So beyond thermodynamical equilibrium. So suppose that all the particles, I said before, are in epsilon 1, and therefore, basically, let me also assume that I can compute the microeconomical partition function to this situation. So I will have the zeta m is minus epsilon 1 divided by so times beta, because the epsilon 2 basically is not occupied. And now if you compute by using the formula of the entropy, the formula of the entropy was Kb n log of zeta m plus E divided by T. If I just substitute this epsilon to this, what I get is Kb m, then I have the log of zeta m, which is minus epsilon 1 beta, plus E, which is n epsilon 1 divided by T. And of course now this must be 0 because beta is 1 divided by kbt, kb cancels and then is equal to 0. Okay, so that means that if all the particles are in epsilon 1, the entropy, which is not the thermodynamical entropy, because I'm considering the situation out of equilibrium, if you want, is basically the Gibbs or Shannon entropy. So if S is equal to 0. Which is also interesting from the interpretation point of view, in the sense that if all the particles are in just in one energy level, then the situation of maximum order, now they are all in the same level. And also, there is only one way to arrange all the particles in one level. Okay, so there is not is far away. I mean, is a situation with the minimal probability. Is actually the opposite as with respect to the maximal probability, which is the thermodynamical equilibrium. Okay, so similarly, if all the particles are in epsilon 2, I get that again S is equal to 0. But this is just a little game, and it's not something that you need to study, just to show what happens beyond thermodynamical equilibrium. Let me switch page. Now, if I consider the situation all in epsilon 1 or all in epsilon 2, in both the cases, the entropy is 0. But the energy is different, because in one case the total energy E is n epsilon 1, whereas in the other case the total energy E is n times epsilon 2. That means since the entropy and the temperature are related by the following equation, NV1 over T, it means that in the configuration in which all the particles are here, by decreasing the number of, by decreasing the energy, the entropy increases. Increase the energy, the entropy increases. Because the entropy is equal to 0 for that specific configuration. Now I remove some particles from state 2 and put them to state 1, so I'm decreasing the energy, but the entropy is increasing because the entropy was 0 in that specific configuration. So if I remove some particles and put them in epsilon 1, I'm increasing the entropy. Therefore, that means that I have negative temperature. Okay, and actually this negative temperature is used, it's a feature of systems with bounded, with spectrum that are bounded from above. Then there are some studies on negative temperature in solid state physics. So this was just to comment on the effect of having a bound spectrum, okay, or unbound spectrum. Okay, so let me go on. let me just present application or exercise of this microeconomical formula, and then we stop for a break. And let us consider the solid, the Einstein solid. Now, I'm pretty sure that you have seen these in other situations, so I will not do the calculations in full details. But now I will, first of all, remind you what is the Einstein solid, and then you will tell me if you have seen these things in other courses, okay? So basically the idea is to consider a crystal with, let's say, 3m, because we are in 3 dimensions. So consider crystals of n particles in 3 dimensions, and suppose that all those particles which are fixed in the lattice points can vibrate in the 3 different directions of space. Therefore, you imagine that you have 3n harmonic oscillators, if n is the number of particles, and assume that they all have a unique fundamental frequency. The same fundamental frequency. That we call nu. That means that the energy of those harmonic oscillators is h nu, with h is the Planck constant, times I plus 1/2. Okay, same for all the 3 oscillators. Okay, so this is a situation similar to what we have described before. Before we had this epsilon I, which were these energy levels with a spectrum which was unbounded from above, and here we have a similar situation, just that epsilon I is proportional to h nu times I plus 1/2. Okay. Now let's just make a first calculation on this, and then we stop for a break. Let's try to compute, first of all, the microeconomical partition function. Zn. So this function was the sum over I of e to the minus beta epsilon I. Okay. Now in this case, this is the sum of I of e to the minus beta, and then I need to introduce epsilon I, which is h nu times I plus 1/2. Okay, which is e to the minus beta h nu divided by 2, and then I have the sum over I of e to the minus beta I h nu. Okay, now this is equal to e to the minus beta h nu divided by 2, and this is a geometrical series for which I know the result, the 1 minus e to the minus beta h nu. Okay, because here I runs from 0 to plus infinity. This is the microeconomical partition function. Okay. Now, from the microeconomical partition function, as we saw before, one can compute the thermodynamics. One can compute the entropy, one can compute the Helmholtz free energy, the energy per particles. And once we have all this quantity, we can do the thermodynamics of this system. Okay. So now let me stop for a moment and let me just ask you if you have seen this in other situations or not. The Einstein solid.
Yes, we did.
Okay. So I will go fast on this, okay? So let's make a break of, let's say, 5 minutes and we will continue.
Va bene, grazie. Posso chiederle una cosa?
Sì, sì.
Io non so se è il mio problema e basta, ma sento la sua voce molto metallica e alle volte perdo qualche parola perché la sento lontana. Non so se la mia connessione è un problema di tutti.
Non
No,
so.
devo dire che anche per me è così.
È
Sì,
metallica?
anche qui è la stessa cosa.
Ok. Allora posso provare a fare una cosa di usare la cuffia, vediamo se funziona meglio, ok? Il microfono.
Va bene, la ringrazio.
Adesso lo prendo e vediamo se funziona meglio.
Ok.
Okay, let's start over. Now, is it a little bit better now, or is the same?
Molto meglio.
Molto meglio. Ok, allora è bene che uso il microfono. Ok. Okay, so so once you have the microeconomical partition function, the system, you can derive all the thermodynamical quantities that you need. The Helmholtz free energy we wrote before is minus kBt, total number of particles, which in this case is 3n because we have 3n oscillators, the log of Zm. So this is the Helmholtz free energy, which can be computed easily by just putting instead of Zm the formula that we had before, and one should get the following result. Then I'm just quoting. Then if you want to try to compute it, it's just a matter of putting the formula there, and that's it. Okay, so yeah, log of minus beta h nu. This is the Helmholtz free energy. Now remember that the Helmholtz free energy can be also from the Helmholtz free energy, one can compute, for instance, the entropy, because dA divided by dt at fixed volume is minus the entropy, and therefore by just doing the derivatives of this quantity with respect to t, we can get the entropy. And so this is an exercise you can try to do. Or you can compute, for instance, E. Well, E can be computed in two ways. Is A plus Ts. Once you have the entropy, temperature, and Helmholtz free energy, you can compute E. Or you can compute E by multiplying the total number of particles times the average energy of the particle. Okay. So when you compute E, let me change paper. You should get the following result, which is known, and of course I'm not spending too much time on that because it's something that you already know. And here h nu beta minus 1. Okay, where this quantity here is called the Planck distribution. And of course, it's something that you have seen also in the case of black body radiation and so on and so forth. Okay, and this is the 0-point energy. Okay. Now, for instance, one thing that one can compute is the specific heat or the heat capacity at fixed temperature, which is the typical quantity that is interesting to compute in this case, which is the derivative of energy with respect to T at fixed volume. And if you do the calculation, it's just computing a derivative. Of course, the 0-point energy does not contribute. And you should get the following result. It's equal to 3n kb. Then I have h nu divided by kbt squared e to the h nu beta divided by e to the h nu beta minus 1. And this can also be done as an exercise if you want to try it. Exercise. And I think it should be correct. Now, there are typically, the discussion now is done on the two limits of this formula. First of all, in the limit in which t goes to plus infinity, Cv scales like 3n kb h nu divided by kbt squared. Then I have a 1 at the numerator, sorry, and at the denominator, since I have an infinitesimal quantity, this infinitesimal quantity, I just expand, no? E to the x minus 1 is proportional to x. And therefore, at the denominator, I just have h nu beta squared, which simplify with this because beta is 1 over kBt. And therefore, I just have 3n kb for the heat capacity, which is Dulong-Petit law. Okay, which is a constant, okay? This holds true also for the ideal gas, which we know that the heat capacity is a constant, okay? But actually correction from quantum mechanics then that we see now in a moment will modify the behavior of the heat capacity at small temperature. Indeed, if T now approaches 0, the exponential actually now will explode, and therefore we will have that CV scales as 3n kb, and then I have an h nu divided by kBt squared, and then I have an exponential of minus h nu beta, okay? This is the scaling of heat capacity when the temperature is approaching 0, okay? So you see that there is a dependence 1 over t squared and then an exponential of 1 over t, which of course is an exponential suppression, okay? Exponential suppression. Okay, so actually we see that the heat capacity gets an exponential suppression in the case of an Einstein solid, which is something which is qualitatively okay, in the sense that we expect indeed that the heat capacity goes to 0 as T approaches 0, because basically all the degrees of freedom are frozen. And so you, even if you provide the heat to the system, you provide the heat to the system, and therefore, if the heat capacity is small, then the temperature will change a lot, because it's very, so to say, easy to change the temperature of the system. No, if the heat capacity is small, if all the it's easy to excite the harmonic oscillators. Okay, that's the meaning. Although the exponential suppression is too fast, and actually you probably know that actually the correct behavior is that the heat capacity should scale as T to the power of 3 for the real solid, which is the Debye model of solids. Okay, so let me write it down. Actually, it must scales as T cubed in the model which is called the Debye model. But I'm pretty sure that you do this, you have done this, or you will do this in the course of structure of matter or solid state physics. So I will not comment much on that. Okay. Okay. Okay, so this was the link between the microphysics and thermodynamics. And we basically, the link is actually provided by the Boltzmann entropy, of course. The Boltzmann entropy is also telling us that the most probable configuration is actually dominating the phase space, if you want. So computing all the possible configuration or computing just the most probable one provides the same thermodynamics, okay? Now the question is, and we will touch this topic just for, let's see, a couple of hours or maybe a little bit more, is which is a typical topic of statistical mechanics. So how equilibrium is approached, how to describe the way a system
Dovrebbe
approaches.
cambiare la pagina, scusa.
Hai ragione, grazie. How to describe the way a system approaches equilibrium. Well, this is thermodynamical equilibrium, of course. And in particular, what we will see is the case in which we do not have a localized and independent system, but we'll consider another system now, which is a gas of particles in a certain volume, V. Suppose that these particles are classical particles. Namely, one can define the position and the momentum of those particles. Suppose that, so being classical, they are also distinguishable. I suppose that the interaction are now interacting with point interactions. Which means that the two particles interact with each other when they are very close by, okay? So basically, if they are in the same position in space. And another assumption that we will do is that the system is dilute, okay? Dilute system. So that the density is not too large. Actually, to define a dilute system, it would be better to introduce the thermal wavelength, which will not, which we cannot introduce at this level. But let's just consider this dilute system as a situation in which the density is small and the effects of quantum mechanics can be neglected. So what we will see, what we will derive is what is called Boltzmann equation, which is a tool to describe exactly what we said before, the approaching of a system to equilibrium, a system of particles interacting, classical particles, dilute, and how from a situation which is out of equilibrium, out of thermodynamical equilibrium, we at the end up with a configuration of thermodynamical equilibrium. So the Boltzmann equation is let's say a tool to describe the approaching to equilibrium and to basically try to provide an explanation for the law of increase of entropy, for the second law of thermodynamics. Because what we have already seen sometimes is that the situation of maximal entropy, which is the situation of thermodynamical equilibrium,
is okay, is that one, but we can define also somehow the entropy, which is called Gibbs or Shannon entropy, in situation in which we are out of equilibrium. And it seems clear that in those situations the entropy is small, okay? Actually, in the example of the K levels, the smallest possibility for the entropy was entropy equal to 0, which was corresponding to Pi equal 1 and all the others Pi equal to 0, okay? But actually the situation of thermodynamical equilibrium is just the opposite. It's just the situation in which all the probabilities are the same, and in that case we have the maximal entropy, and in that case the Boltzmann entropy would correspond to the entropy of the most probable configuration, okay? So now we want to somehow infer which is the way the system approaches equilibrium but now in a real volume with real particles and so on and so forth, okay? And the tool we will try to derive is the Boltzmann equation, which is a very complicated equation, which is anyway used to very much also recently in research for doing astrophysics or heavy ion physics and so on and so forth, okay? So now, to introduce this tool, let's try first of all to introduce the space in which we are. Suppose that we are in a space that we call mu, which is a space of six dimensions, in which three of those axes are basically the three axes of position, and the other three are the axes of momentum, the components of the momentum. So let's try to just consider two axes, x and px, okay? Where x, y, z, px, py, pz are the components or the position and the components of the momenta of the particles, okay? And now let us consider a small volume, infinitesimal volume, of mu, which will be dr times dp, which could be a box in this plot, two-dimensional plot, okay? Now, suppose that in this small volume, suppose that we have dn particles, so number of particles in a infinitesimal volume, dr dp, and let us define a function, which is a function that we call f of r p, and in general also time dr dp. Now f is called distribution function, and basically it's telling, this function is telling me if I want to count the number of particles in a small volume drdp centered in a position r and p of the mu space, how many particles I have, okay? So basically it's a way to count. It allows to count the number of particles with position between r and r plus dr, and momentum p and p plus dp, okay? Now, in principle, these distribution functions depends on space, depends on momentum, and depends on time also, okay? Well, actually, the goal of the Boltzmann equation will be to derive an equation to find f, which is the distribution function. Let me change page. Suppose for a moment in one limit that there is no interaction between particles. There is not interparticle interaction. But suppose instead that there is a force F, external force, which could be an electric field, for instance, a gravity field, which is a function of R. So it could be a field. It depends on space, and suppose also that this field does not depend on the momentum of the particle or on time, because in that case we will have dissipative formula that we are neglecting in this case. Now, suppose that the number of particles is conserved, and let us ask ourselves what happens once we follow a certain number of particles in a volume. What will happen as an effect of this external field? Okay, so by assuming the conservation of number of particles, suppose that I had dn particles around R and P, and this dn is f of Rp t, and we impose that this is equal to f of R plus v dt. So in time, so what we are going to basically write is how many particles we will have as due to the, so we are imposing that the total number of particles in this small volume is conserved as a function of time. So therefore, this, sorry, here there is something missing. Let me write it again, sorry. So this f of R, P, and T, dr, dp. And we impose that this is equal to the distribution computed at a time t plus dt. And of course, when I run the time, R will go to R plus V dt, which is actually R plus F divided by M, sorry, P divided by M dt, and the momentum will go to P plus F delta t. So then this function will be a function of R plus the incremental of R, which is P divided by M times dt. Here I have a P plus F dt, and here the time is T plus dt. And in principle, the volume, the shape of the volume is this different, dr prime and dp prime. Okay, so basically what I'm saying is that as due to the external field, if I look at the evolution in the temporal evolution of the system, since the Boltzmann equation is just basically the aim of this equation is to derive the temporal evolution of a system which is approaching equilibrium. Here I'm just conserving the number of particles. I had dn number of particles at time t, and imposing that the same number of particles is preserved at a time t plus dt, whereas due to the running of time, the distribution now will depend on R plus P divided by M dt, P plus F dt, T plus dt, and also the volume in principle could change. Okay. Now, what is the relation between dr and dp? dr prime, sorry, and dp prime relation with dr and dp. Well, actually, this is easy because the transformation of r and p are the following. So r prime is r plus p divided by m delta t, and p prime is equal to p plus f delta t. Okay. Therefore, take just the x components. Consider the x components. Therefore, x prime will be x plus px divided by m delta t, and the px prime will be px plus fx delta t. Okay. Now what I have to do is to compute the Jacobian, no? So dr prime dp prime in general is the Jacobian dr dp, because I'm changing variables basically. Okay, so this is Jacobian. For two dimensions, for the case of just x, then one can do the calculation of in 3 plus 3 dimensions, but let us consider just this case because it's easier. So here the Jacobian must contain the derivative of x prime with respect to x, derivative of x prime with respect to px, derivative of px prime with respect to x, derivative of px prime with respect to px. And once you do the calculation by using this formula here, you see that here you have 1, 1, and there you have delta t divided by m, and here you will have a derivative of f with respect to x delta t. Okay, which will be equal or almost equal to 1 minus something delta squared. I have a delta squared. So at leading order, this Jacobian is equal to 1 for an infinitesimal amount of time. That means that dr prime dp prime is almost equal to dr dp, at least if delta t is small. Okay, and therefore we can conclude, let me change page. We can conclude that f of r plus p divided by m delta t, p plus f delta t, t plus delta t, since the infinitesimal volumes are the same for what we have just derived, this function here must be equal to the f of r p t. Now you expand this, a leading order, so you will have a leading order f of r p t, and then you have the first derivative times the differential and a partial derivative. Okay, so basically you basically have this, no? So this will be f of r p t plus the df dt. This is the total derivative, plus derivative of f, well, actually this is a gradient of f with respect to the variable r, quindi position gradient, scalar p m, okay, plus then I have a gradient with respect to the momentum of f scalar f. So this momentum gradient. Well, plus other terms, and this is equal to f of rp t. Okay, which then means that the total derivative of f is equal to 0, and this is equal to derivative of f with respect to time plus the gradient r of f scalar p divided by m plus the gradient p of f scalar f is equal to 0. Now this is called the Boltzmann equation also in the case in which there is no interaction between particles. Basically, this is telling us that the total derivative of the distribution function is equal to 0 in the case in which there is no loss of particles and there is no interaction among the particles, but just in principle an external field. Okay. Now, the thing is that now we have introduced the interactions, and to introduce interaction, this is done in an empirical way. So to introduce interaction, one does the following trick. We write df dt plus gradient r of f scalar p divided by m plus gradient p of f scalar f. This is a total derivative. We impose, well, Boltzmann imposes that this is now a term which is called the collisional term, df dt col, which is called collisional term. This collisional term takes into account the change of f as due to the interaction between particles. Okay? At this level is nothing but a letter, okay? But it must be 1 over the dimension must be of course a dimension of f divided by a time. So then that's why it's called df dt. And somehow in this quantity we need to introduce the interactions between particles. Indeed, let's write df dt col as a sort of difference of rate.
Prof.
Sì, io non ho cambiato pagina, grazie. Where let's try to see what are those two R bar and R. So R bar is as the following interpretation. R bar times delta T times dr times dp. What does this term? Number of collisions between time t and t plus delta t, for which after the collision one of the two particles has momentum and position, so position and momentum between r plus dr and p plus dp. First of all, only binary collisions are considered, at least in the Boltzmann equation. Then there are a generalization in which one can have also three-body collisions and many-body collisions. And basically, what is doing this term r bar delta t dr dp, it counts the number of collisions that adds particles in the volume dr dp centered around r and p as due to the collisions. Okay, so it's the refilling, if you want, of particles as due to collisions in the volume dr dp centered in r and p. Okay. So this is after the collision. So how many particles, if you want, enter in this volume? Now, similarly, that's why there is a plus here, because R bar will increase F, so increase the distribution, because increase the number of particles in that specific volume of mu. Similarly, R instead delta t dr dp does similar thing, but it counts the number of collisions between t and t plus delta t, for which before the collision one of the two particles had position and momentum between r and r plus dr and p plus dp. Okay, therefore the difference between r bar and r is basically the net number of particles that is in the volume centered in r and p with dr dp as infinitesimal size of this volume. Okay, so basically suppose that this is the volume of the mu space, infinitesimal volume of mu space, with a position which is r, a center, if you want, which is r and p. Of course, some particles will enter in this volume as due to the collision, but some other particles would flow out of this volume as due to the collision. Okay, in and out. So the R bar counts the number entering this volume, whereas R counts the number of particles X which are going out of this volume as due to the collisions. Okay. Now the thing is that we need to compute, or at least to make a formal, try to find a formal expression for those particles, and this is what we will try to do. So let's take a binary collision. In general, I will have a conservation of energy and momentum. Let's try to write P, the conservation of momentum, as P plus P2 is going and equal to P1 prime
Però
plus...
scusi il foglio.
Non ho cambiato il foglio, certo. Scusate, ma questa cosa ancora non mi sono abituato. Ok, so let's take a binary collision in which a particle with momentum P collides with a particle with momentum P2, and at the end, these two particles, we will have momenta P1 prime, P2 prime. Now, here I'm talking about elastic collision. And all the particles are the same. Okay, so I just have an exchange of energy or exchange of momentum, actually. Okay, energy and momentum depends on the frame. Where P belongs to the volume, the small volume dr dp centered around P and PR. Okay. So, for instance, in this situation, I have one particle which is in the initial volume dr dp, and then which is interacting with another particle belonging to another volume element, and then I will have a final momentum P1 prime, P2 prime. So this calculation is useful for computing R, not R bar. Now let us introduce a function f. Okay, first of all, the two particles interact if they are in the same position. R, okay? Because I'm pursuing a point-like interactions. So then they interact only if they are exactly in the same position. And let us introduce a function f, which is a function of R, P, P2, and T, such as dn is equal to f of R, P, P2, and T times dr dp dt, sorry, dr dp dp2, similarly for the small f. And basically this function, which is a correlation function, counts the number of particles, the number of pairs, if you want, of particles, counts the number of pairs of particles that in the position are between R and R plus dr, and have momenta between P and P plus dp and P2 and P2 plus dp2 and P2 plus dp2. So it's a two-body correlation function. Why I need to introduce, I will stop here, this function, because I know that I need to introduce the cross-section at some point, or a matrix element of the interaction, which is completely unknown, and we will just treat as a symbol. But somehow the rate of particles entering and exiting this volume must be proportional to some matrix element which describes the interaction, times the flux, if you want. Similar to the calculation of the cross-section. In a cross-section calculation, one needs to introduce the number of targets and the number and the flux of the particles, no? For instance. So here, similarly, we have to see, first of all, which is the microscopic interaction matrix element, and we will write as a letter, basically. We will not go into the detail. But then this matrix element must somehow be multiplied by the number of particles colliding, basically, you know, as we do in the cross-section calculation. And then I have to count, and then I have to consider the conservation of energy and the conservation of momentum. Okay, so what we will see next time is that we can provide a formula for R and R bar in terms of the microphysics, which will be actually hidden in this calculation. Okay. And at the end, we will do an hypothesis, which is the fundamental hypothesis that Boltzmann did, which is the hypothesis of molecular chaos. So I will stop here because it is 1, and if there are questions, otherwise let's continue on next Thursday. Ok? Se non ci sono domande, io chiuderei. Va bene.
Va bene,
Arrivederci.
grazie, arrivederci.
Salve. Salve.
Arrivederci.
Arrivederci.